Okay, good afternoon, everyone, and welcome to the second edition of Redlab Live Talk. We are very happy to start this live event, which has been organized to keep you informed about the Redlab ongoing projects and latest initiatives, and to learn more about the interns experience, which will delight us today with their presentations. This event is divided in 4 slots: an introductory part, a keynote, a part dedicated to research activities, and a final part dedicated to the interns presentations. Please also be informed that this session will be recorded and will be soon available on the Circo Hub. If you have any questions, we kindly invite you to write them down and ask them at the end of every presentation. I will now give the floor to Gianmaria Giaconia. Thank you.
Thank you very much, Viviana. Thanks, Rafael, and thanks, Barbara, for setting this up. And thanks for all the audience and all the people attending the Redlab talk, which I believe is one of the most strategic initiative at Circo. I promise we won't let you down because we get a lot of interesting things and news in the Redlab. And of course, I want to share you with all of you today afternoon. Let me thanks also and also apologies from our general manager, Roberto, who couldn't do this introduction and asked me to do it as a co-manager of Redlab. As you probably know, in June, I believe it happens, Roberto once wanted to give to the Redlab, which is doing great things in terms of research and relation with university, an additional help to create the liaison between the Redlab and also the market, what is happening out there. So that's the reason why I'm joining the Redlab. It's a great honor for me, of course, to be here with you today and explaining what could be the next things the Redlab could do in the future. As you see from the slides that Rafael is showing, Redlab so far did a lot of things, provided unique research opportunity for students, improved the collaboration between university and the research centers, is also supporting our Circo operation in our existing contracts. Sometimes we have R&D needs that needs to be satisfied, and Redlab is going and helping, supporting with dedicated activities. However, we are thinking to do something more. We want the Redlab to do more, to be more. So in the next future, we would like the Redlab really to become the strategic initiative to boost innovation. And how do we boost innovation? We have to listen what the market trends and what are the market needs in the space economy in the near future, and we need to anticipate those needs. So by anticipating what will be the needs, we will start developing what is needed tomorrow, not what is needed now. That means being proactive. Of course, we are working in some cases as a reactive. In some contracts, there are some R&D needed, and we can leverage on our relationship with university, which is fine. But the idea is to really understand and develop and start researching what will be needed in the future. And this could be done only thanks to the cooperation with university, but also with the cooperation with startup and SME acting as an incubators. That's my introduction, and then I will be glad to explain a little bit more further. Thank you very much.
Thank you, Gianmaria.
Thank you, Gianmaria. I will now give the floor to Raffaele Crappolicchio. Thank you.
Yes, good morning, everyone. I'm introducing the Redlab and the live talk number 2. So, as mentioned already by Gianmaria, Redlab is a very strategic initiative to full innovation in Circo Italia. And so that is the reason why we have the Redlab is our research and development laboratory. This initiative has started in Italy at beginning 2020 and was announced formally to the media in October 2020 with some with news in the main space with Space Daily Space Earth Observation Journal. Why the name of Redlab? Why red? Red is a circle brand color, and it's color that communicates passion. And so in our mind, the Red Lab is a place where people are passionate for research and innovation. We are working on Earth observation, and our research activity are split in 4 main strategic domains, which are Earth science, Earth observation sensors, Space 4.0, management, and engineering. Which are the opportunities that we give to the student? The first one is to do curricular internship with us. So we are providing grants for students to obtain the first and second level master or post-degree master degree with a duration between 9 and 12 months. We have also planned to offer grants for young researchers for industrial PhD with a duration of 3 years. We also offer internship, so grants for postmaster and young scientists with duration of 6 months. But we have also opportunity for our staff. So that's also, we also like to invite our staff to be part of the Red Lab. And so what I get out of being a Red Lab, for sure you have opportunity to make network with other colleagues and with university and research institutes. Develop your own research ideas, acquire new skills, learn new process, work in a team where the goals are decided together. What are the resources that the Red Lab has to do the research activities? First of all, the tutors. So there are people in our colleagues that are tutors for the student and follow up the research. Then we have this kind of talk, live talk, in which the researchers put together, and so you can share what you are doing and with the live talk. Then we have a Red Lab project website where we put news, we announce the open research call. We have a platform to process and to access the data. We have the on our availability and on the OnDias platform, some virtual machine to process the data, to test your algorithm. And then we have also a YouTube channel. It's where you can find our videos, the Red Lab live talk, and all the material that is produced to communicate our activities. Now I will just want to talk a little bit about the Red Lab objectives, and basically match these objectives with the agenda of today, because the agenda of today is built around our objectives. And of course, the first object for us is to prototype new service application to develop a new business opportunity, as mentioned before by Gian Maria. Also improve Red Lab visibility in the scientific community as an expert laboratory. So this will be done via workshop, presentation, peer-reviewed papers. And an example of this will be the keynote from Enrico Cadao, which will explain how we have just a new type of business and activity in the hyperspectral data scientific exploitation projects. The second objective of Red Lab is to enable research and innovation for operational contracts and business development, to augment science foundation for operational service activities by core expert science team, foster staff engagement in Red Lab activities. And this is about the talk of the research activities. So these activities are basically coming from our operational contract, and people working this operational contract are also able to do interesting research activities, and we would like to show some outcome from Gabriele and Marco. And the last point is, of course, Red Lab aims to have a strong relationship and partnership with research center and in university. And to do this, we offer some internship opportunity with us. And this is also the third block of the presentation in this live talk. It's the research internship that we have done with Marianne, with the University of Bologna, Federico, and with Tor Vergata University, and with Nicola in the in the framework of the Space Science and Technology Master at Tor Vergata University. Now that's the present, but we also have would like to talk about the future, as mentioned by Gian Maria, how we see the evolution of Redlab. And at that point, I invite Gian Maria to really report on what is our vision for the future and explain what we would like to do in the next stage. So, Gian Maria, you can comment these slides.
Thanks, Raffaele. You said right. You said Redlab it's an opportunity, and I want people see Redlab as an opportunity. I want they recognize in the Redlab where they as a place where they can develop their own ideas, where they can challenge the existing process, where they can suggest new process and at the same time acquiring new skills. So Redlab is doing great at the moment, but I believe there is still need some little help to be connected to the market, to boost innovation and to transform this research into commercially viable ideas. That's the final scope at the end. It doesn't mean we only need to do what will be commercially viable. No, we will do research at 360 degrees like we always have done. But some of them can be also, let's say, converted into something that will improve the way we deliver our own services, improve the way we are doing current things, and will help us, will allow us to change in better. This new connection with the market, of course, can only happen if is the innovation driving and leading the Redlab activity. That's why we are thinking to restructure a little bit the Redlab to be a real business function which is collecting all the R&D needs coming from we used to call it farmers and hunters, but the idea is that there are R&D needs all over the world. These R&D needs may come from an existing contract, may come from a business opportunity, may come from the mind on an ideas of one of the master or the PhD students, and we have to be able to intercept this idea, and that's why I was thinking about having the ambassador fully and constantly committed in order to analyze and receive the request and decide if there will be a dedicated project for investigating further in this idea. And I was thinking that we should look for the commitment of all the other circle and even not external people, because they need to feel and be part of the Redlab activity, like they are fully committed, and internal circle and external resources all together in this common, let's say, spirit to help the research and help to develop new algorithm, new things that can be, of course, also commercialized. So the idea is then we will be hiring technical leaders, and these technical leaders will take the ownership of the research that will be decided by the ambassador. So that's more or less is in a nutshell, what we are planning to do, and we hope we will succeed in this and having a proper structure for the Redlab. Thank you very much.
Okay, thank you, Gian Maria. Yes, indeed, this evolution it's very, very welcome and hopefully implemented in the next year, 2022.
Yeah.
So that's my last slides. It's just thank you for your attention to this introduction from me and Gian Maria, and enjoy the live talk. Thank you.
Thank you, Gian Maria and Raffaele, for this introduction to Redlab. Following, we now have a keynote with Thank you.
Thank you. Can you hear me?
Perfectly.
Yes.
Okay, so I'm going to share my screen now. Which as well, always it's a bit cumbersome. Okay, here we are. I'm going to put it in full. Can you see my screen correctly?
Yes.
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 Okay. So first of all, thank you for this opportunity to share this this presentation with you. So my name is Enrico Giuseppe Cadao. Most of you already would say know me because I've been working in Serco since 2009. By now, I'm one of the Redlab ambassador, and as well, of course, as most of us, I have also another, hat, acting as a EMSS service manager and working for ESA for many times. This presentation will provide you an overview of a couple of contracts that Serco won together with other, let's say, entities in the framework of the Prisma hyperspectral mission funded by the Italian Space Agency. So just a bit of context, Prisma is medium resolution hyperspectral imaging mission, as already said, founded by ASI, which was successfully launched in 2019. Prisma stands for Precursore Iperspettrale della Missione Applicativa. It's a mission that personally I was expecting since 2010. So and then, of course, as usually happens in the space fields, there has been a lot of delays, but finally the mission was successfully launched two years ago. So the main fields of expected benefit of this hyperspectral data can be summarized in this list. So for sure there will be a lot of forest analysis exploitation projects, so forest fires, forest classification, biomass analysis, and so on. As well, there will be a great contribution to the precise farming, so precision agriculture in terms of crop mapping, rotation, stress analysis, and so on. But also a lot of application dealing with inland and coastal waters, so water quality, chlorophyll monitoring, algal bloom, etc. In addition, also climate change and environmental research. So, for instance, desertification, deforestation, environmental degradation and hazards, and then all the list of applications which are dealing with the soil degradation and soil properties. For instance, the analysis of mining areas and so on. This table just provides you, let's say, an overview of the main characteristics of the Prisma sensor. So the first thing that maybe it's more important, it's the number of spectral bands that are available. So the people that are usually are let's say working with the multispectral data products are used to work with the maximum 10 or 12 spectral bands. Here in the hyperspectral domain, we are dealing with more than 200 of spectral bands. So this means that there are a lot of more information to be handled, information which, of course, has to be properly, let's say, exploited and processed. The spatial resolution is at 30 meters at nadir, but there is also a panchromatic channel at 5 meters of resolution. in 2020, ASI issued a public invitation to tender for the scientific exploitation of Prisma data products. So one of the main prerequisites of, let's say, this ITT was that the consortium must be led by research entities, so university and research centers. So CERCO participated in 2 different consortia, one that was led by the University of Tor Vergata and one by La Sapienza University of Rome, by providing, of course, scientific and engineering support. On this, I have to say that also the ONDA platform was successfully proposed and I have to say also appreciated by the evaluators. Both the projects submitted were selected and awarded by ASI, and now the kickoff, I think it's going to be to happen sometime in January 2022. So they were postponed several times, but I think now it's time to start. I'm going now to briefly explain the 2 projects, so where CERCO is involved. So the first one is called Primary, which stands for Prisma for monitoring air quality. The main scientific goal of this project was it's to obtain qualitative and quantitative information of the particulate matter, so the famous PM at urban scale. In particular, the idea is to discriminate between the anthropic polluting particulate matter and the natural one. For instance, the desert silt and dust that often is affecting our peninsula. On the left, you can see the logos of the various components of the consortia. So there is the University of Vergata, which is leading the consortium. Then there is University of L'Aquila, 2 different departments of the CNR, so the ISAC and IAA, and of course the prime. It's I mean, as it's the entity which is let's say steering the project. More in detail, so this is just the roadmap of this project. So the idea is to generate atmospheric profiles containing meaningful statistics of the variable of interest, starting from CAMS and geoscams data source. There will be a phase for simulating the Prisma data corresponding to the generated profiles. There will be also a bit of AI algorithm for real data inversion. And then finally, we will generate the final products using Prisma data. There will be also, of course, a huge phase of test validation and sensitiveness analysis, but also that data collected from UAV and in situ data sensors will be used. For instance, the Bakunin project, it's will be a great contributor to this phase of the project. This is just a roadmap. Sorry, the slide it's in Italian, but basically it's just to give you the context of how the different phase of the project will be tackled. This is just an example of the foreseen products that we aim at generating. So you can see that the most important thing to highlight here is the different resolution that we aim at reach at the end. So starting from approximately 70 kilometers of resolution of the CAMS reanalysis data, we try to reach 30 meters of resolution of the final primary output product. So the idea is indeed to go at urban scale for determining and assessing the source of the PM in the area of the Provincia di Roma. The other project, which is called ClearUp, which stands for Control of Landfill Environmental Assessment Research using Prisma. It's another project led by Sapienza University of Rome with other partners. For instance, there is Eurosoft, which is a small company from Naples, the CNR, IMA, Tor Vergata as well, and of course Serco. Here the main scientific goal is to exploit the Prisma data in order to promptly detect soil contamination due to the presence of legal or uncontrolled waste management practices. So it's a project more focused on the soil contamination aspect, and for instance, to promptly detect critical aspect linked to the waste management system. So the project will use Prisma and Sentinel-2 data product for generating relevant contamination indexes over susceptible areas. The roadmap as well here, there will be user requirement collection. Mostly the users which will be involved are located in Campania region for let's say historical reasons. There will be a study and development of Earth observation algorithm devoted to the generation of soil contamination indexes starting from multispectral and hyperspectral data. Then there will be the creation and population of a dedicated data cube that will merge all this data in a data cube. And then, of course, the integration and the validation of the prototype, as well as the transfer to the users of the final products for testing. This is just the architecture of this project. So you see that there is also Onda that will accommodate all the different, let's say, elements of the project. So starting from the archive of the source data, then the generation of the data cube, the running of the processors, and then there will be the graphic user interface for disseminating this data to the relevant users. Here, just an example of what we aimed up to do. So there will be a multi-temporal soil contamination monitoring using vegetation indexes, because the contamination is usually promptly detected using vegetation indexes, because the vegetation is affected by the contamination of the soil. And as well as we aim at use Sentinel-2 data products for identify suspicious thermal anomalies, which very often in such area are linked to, you can see these pictures, uncontrolled waste management practices by the people. Just few details and schedules of this project. So the project direction, it's 2 years. There will be a regular progress meeting with the Italian Space Agency. There will be participation to scientific conferences, and as already said, the kickoff now is foreseen in January 2022. As already said by Gian Maria and Raffaele, these 2 projects will open some Redlab opportunities that could be stages, internship, or a PhD, of course, to be discussed once the kickoff will be held in the beginning of next year. And that concludes my presentation. So thank you for your attention.
Thank you, Enrico. If you have any questions, and or to write them down.
Okay.
Enrico, one question from my side. What is the envisaged? Yes, what is the envisaged support from Serco in the first project?
You mean in terms of activities?
Yes, in terms of activities.
Yeah, we are leading 2 work packages in detail. One will focus on the generation of a sort of matchup database between in situ measurements and satellite overpasses. So there we are going to generate a sort of iterative database that will show, let's say, the exact matchups between the satellite overpasses and the in situ measurements available, for instance, over in Bakunin. Then there is also another work package more, let's say, related to integration and validation of the processors within the owned ecosystem.
Okay, thank you.
Thank you, Enrico and Raffaele. Let's now pass to the third part of this event, I am now pleased to introduce Gabriele Meri.
Okay, can you listen to me?
Yes.
Okay, and just share the screen and the presentation. Okay. Can you see the presentation?
Yes.
Okay. Thank you for the invitation. I'm here to present to you some a specific study that we done in Bakunin, and in particular the measurements of NO2 collected in Rome in years 2020 and 2021. We briefly see the results and the comparison with historical data series. First of all, I briefly introduce you the Bakunin supersite. Bakunin is a circle project founded by ESA in collaboration that collaborates with several scientific institutions such as Sapienza University of Rome and the CNR, and is the acronym of Boundary Layer Air Quality Analysis using Network of Instruments. And the Bakunin supersite is composed primarily by three measurement sites that, as you can see in this picture, in this map of the Roma region. The three sites are the first
Gabriele,
one. Yes.
Can you please put in presentation mode? Because...
Okay, just a second, please. We have some problem with the condivision. Now you can see at full screen.
Yes.
Okay. I was talking about the three sites of Bakunin. The first one is in Sapienza, in the Sapienza University, in the physics department. That is about in the center of Rome, is an urban site, and also several instruments, the major part of the Bakunin instrument set. A second site is at CNR Isaac in the northeast of the city, and in a semi-rural environment. And the third site is at CNR EEA in the northeast along the Tiber Valley, and that can be considered a rural site. We have several measurements of aerosols, trace gases, turbulence. We perform urban boundary layer studies. We study the sea breeze, the pollution, and the climatology of the urban environment of Rome. Bakunin is a cross point for several networks, such as Aeronet, Pandora Global Network, Aeroskyrad, and Debunet. And we have many instruments that you can see for an example in this picture. For example, here we have the sun photometers, the Chuprede, the Pandora, this instrument that is pointing at the zenith, and the CML. We have the pyranometers, SODAR, a LiDAR, two LiDARs. In this picture, you can see the Pandora is installed at CNR Isaac. And Bakunin perform CalVal activities, and his data are distributed to AVDC through in GEMS format. In this talk, I introduce you to the NO2, that is one of the principal pollutants that affect the city. In this map, you can see the concentration of NO2 in the several important cities in Europe. Here we have Rome. We have a very high concentration of NO2, more than 50 microgram per meter cube. And NO2 is produced by fuel combustion and removed from photochemical reactions in atmosphere. It has a Hemi-life of 2-6 hours and in summer and 12-24 hours in winter. In particular, as we can see in this picture that is taken from the Europe Air Quality Report of 2019, is the main source of NO2 is this gray bar, is the urban traffic, in particular the road transport. The NO2 is usually studied through satellite observation that are average over a medium-long time interval. However, these take several problems. In fact, the spatial resolution of this kind of study is too low to allow the distinction of what happens in nearby measurement sites with different features. As example, here we can see a measurement taken in Bakunin during a plant fire. In blue, you can see the average measurements for that month. And in red, the actual measurement taken when the fire reaches the measurement site. As you can see, the values are very high with respect of the measurement average. And also, the historical data series are too limited to allow a systematic study for satellite measurements. And last one, the temporal limitation of satellite overpass does not allow to characterize the NO2 daily cycle. For this, we have the Pandoras. These sun photometers. The Pandora are instruments that observe the sun and the diffuse light with several measurement techniques, and extract some information about the principal constituent of pollution in atmosphere, in particular the NO2. We have three main variables that are measured by Pandoras. The first one is the vertical column density. That is the total column amount between the altitude of the instrument and the top of the atmosphere, and that is measured in Dobson. Is observed through the direct sun measurement, observing directly the light from the sun. And other two parameters, the tropospheric column density, that is the column amount of NO2 in the troposphere, that is collected using the Max-Doas technique. Max-Doas is a specific technique that implies to observe the atmosphere, the diffuse radiation in atmosphere at several azimuthal angles. And at last, we measure the near surface NO2 concentration. That is the concentration of this molecule near the ground surface, and is measured in part per billion using the Max-Doas technique. We have data collected in Bakunin until 2016 for both Bakunin APL and Bakunin ISAC. In particular, the APL dataset is composed by observation from two different Pandoras. We merge together to this data to form a coherent dataset, and before to do this operation, we perform an intercomparison campaign that assure us that the two instruments are self-consistent and have a very strong correlation, as you can see in these two graphs in the bottom right of the screen, that are the results of the two intercomparison campaigns. Okay. The 2020 and the 2021 are two very peculiar years, as due to the COVID restriction that constrained the Italian government to unprecedented action to face the pandemic. We experienced unprecedented restriction of mobility, and this caused a very huge reduction of traffic. that drops, as you can see from this picture, from a study of Cristiana Bassani, that drops to unprecedented level, as you can see in these two last picture from 10th of April 2020 and 24th of April 2020. This sharp decline of NO2 reaches minus 43% and minus 44% according to Tropomi and in situ measurement data for the urban environment, and minus 17% and minus 20% for rural environment. In particular, this is a graph that represents the traffic reduction obtained monitoring the use of mobile application that use a mobile application that are installed in the phones, and give us an idea of the strong reduction of for urban traffic. In particular, we have this green data from the Apple application that measure minus 80% during the months from March to May 2020. This data have been collected and aggregated over the whole area comprised in the municipality of Rome, and are referenced to the period immediately preceding the lockdown from 13th of January to 17th of February 2020. So in this period in Bakunin, we decided to use our NO2 measurement to perform a live monitoring of the NO2 situation over Rome. To do this, we need to build a reference climatology with the data collected in the years from 2016 to 2019. We decided to build these reference lookup tables that are represented in these graphs. A lookup table is this lookup table represents the average day for each month of the year. You can see here for example, January, and each beans of this graph represent the average values of the measurement collected during January, for example, from 7 universal time to 8 universal time. We have these tables for all the three parameters measured by Pandoras: the vertical column density, these first two, for Bakunin APL and for Bakunin ISAC, the tropospheric column density for Bakunin APL and Bakunin ISAC, and the surface concentration for Bakunin APL and Bakunin ISAC. The most relevant feature is that we can recognize from these schemes is the peculiar shift of the NO2 peaks during the season. In particular, we have a peak in the afternoon, the first afternoon in the winter months, and a peak in the morning in the summer. This is due to the peculiar reaction of NO2 with the wind and sunlight. We build two different kinds of lookup table, one for work days and the second one for weekends. The work days are from Monday to Friday, and weekends are Saturday, Sundays, and the festivities. These allow us to perform a correct comparison even during the weekends, in which the traffic is lower with respect of the other days of the week. Okay. In this picture we can see the 12 tables that we built for this study. On the left you can see the weekend lookup tables, and in the right the work days lookup table. As expected, during the weekend the values of NO2 are lower. Just another things. These blank spaces are caused by the fact that the Pandoras need the sun to perform the measurement. So in the winter, the measurements are taken from dawn to dusk. So we have no measurement during night. When we after we build up these lookup tables, we had to face a problem. In fact, we have the measurement disposition along the day depends on the presence of clouds in the field of view of the instruments, and these affect the data quality. This causes the fact that, for example, during a cloudy day, we can have, as you can see in this picture, we can have some measurements, for example, in the morning, then a stop, and no measurements until the afternoon. The measurements here are presented by these red dots, while this shaded area is the average for that day. This can introduce a problem in our measure. This incomplete sampling could significantly influence the deviation with respect to the reference if not accounted for. For this, we decided to perform a peculiar algorithm to perform the comparison with the historical data series. For each day, we screen the data, assuring that we use only high quality and medium quality data collected by Pandoras. Then we analyze we classify the days as workday or weekend. We then choose the right lookup table, and from the lookup table columns, we calculate the reference daily cycle. The reference daily cycle is the measurement for that the measurement collected for the data at each hour, interpolated to the selected day. To better explain, each one of these columns are associated of the 15th of the month. For example, this column is associated to the 15th of March, and this to the 15th of April. For example, if we collected data on the 1st of April, we perform a linear interpolation between the data taken from these columns and from this one. When we calculated the reference daily cycle, we interpolated another time this data to select the actual times in which measurement of the selected day have been performed. In the case I report in this picture, for example, we should have used just the morning measurement and the afternoon measurement, discarding all measurement collected from, for example, 10 to 16 p.m. to 16 universal time of the reference daily cycle. We call this the ensemble of measurements selected in this way interpolated reference daily cycle. At last, we compare directly the values of this interpolated reference daily cycle with the actual retrieval results of the instruments. And we create this kind of graphs. Here you can see an example of two results of the data collected by Bakunin Pandoras during 2020. In particular, you can see the NO2 tropospheric vertical column of atmospheric of APL, of Bakunin APL on the left, and of Bakunin CNR RISAC on the right. These red dots are the average measurements of the day, while the red bars represent the standard deviation of the measurements summed in quadrature with the average uncertainty of the measurements. This gives us an idea of the fluctuation and of the uncertainties of the measurement for that day. The blue line represents the values of the interpolated reference daily cycle average. For example, you can see this oscillation because during the weekend we use the lookup table, the weekend lookup tables instead of workdays lookup table. The shaded blue area represents the reference variability, that are the standard deviation of the climatology calculated with the lookup tables. This black line represents some important event during 2020. This first line is the coming up of the COVID restriction, and then the publishing of several DPCM that strengthening the mobility constraint during the day. This last line represents the end of the restriction on 15th of June 2020. Observing the data for APL and CNR-ISAC and comparing with this blue line, we can build these two kinds of graphs. These are the variation of the concentration of NO2 with respect of the reference daily cycle. In particular, you can see that the data are after the publication of the COVID restriction are all below the expected values that are represented by this blue line. These shaded area are the variability of the climatology again. In particular, we reach the values of -75% of NO2 reduction during April 2020, and for both Bakunin APL and Bakunin CNR-ISAC. You can see also that the measurement of CNR-ISAC ends on the first days of November. This is caused by the fact that we have some problem with the instruments, and we need to dismantle it for refurbishment. In this table are summarized the average results for the NO2 results for the lockdown period from 9th of March to 15th of June 2020. In particular, we measure an average reduction of -45% with a standard deviation of 20% for tropospheric vertical column in both at atmospheric physical at APL, and -49% at CNR-ISAC, -37% and -38% for vertical column density, and -37% and -29% for APL and CNR-ISAC respectively for surface concentration. In the next slide, there are the same graphs built from NO2 vertical column density. Here we can see that the variation with respect of the reference values are reached just -50%. This is due because the vertical column density takes into account all the contributes of NO2 from the stratosphere and the upper part of troposphere that are not affected by the variation in the mobility circulation. And at last, you can see this graph representing the values obtained for surface concentration in both APL and CNR-ISAC. As you can see, the surface concentration measured at CNR-ISAC after the 15th of June is affected by a huge variability and a huge uncertainty. This is the reason why we decided at a certain point to dismount the instrument and to ship to the builder for the refurbishment. This data, to correctly understand this data, we need to analyze the meteorological background of that period of the year. Here you can see the data from wind speed collected near Sapienza University, near RPL. In particular, we can see that the wind speed was below the expected value for the major part of the period characterized by the stronger mobility limitation, but within the natural variability of the wind. These data are analyzed using the same scheme of the previous data. So the strong reduction that we measured could not be imputed just to, for example, a stronger wind speed. And for that period, we have also a lower rainfall and higher temperature with respect to the monthly average of the period 1971-2021. To be sure that our data are consistent with other measurements collected in Rome, we perform a comparison with the data from the ARPA network. ARPA is the Regional Environment Protection Agency of Lazio, and it has a network of air quality station along all the Rome municipality. In particular, here you can see a list of the station used in this kind of work. And we calculate for each one of these stations the reference value using data from 1st January to 31 December 2019, using the same approach for our Pandora's data. We select all the stations located within a radius of 8 kilometers from APL and CNR-ISAC measurement, and we average data together to create a unique dataset to be compared with our results. Here you can see the station from this parenthesis, the station selected for APL and those selected for CNR-ISAC. And although we have different measurements from these two kinds of instruments, the Pandora measure we use in this study the surface concentration measurement that are taken, however, from an instrument that is installed on the roof of a six-floor buildings, and we compare with the measurement from stations that are at the street level. However, the variation with respect of the respective of the climatology shows an excellent agreement. In particular, for data, here we can see the data in blue of collected at APL, and in red the ARPA data with the respective standard deviation in the blue shaded area and the red shaded area. We can see the reduction measured from both kind of the instrument during the lockdown and during the months after the end of the restriction. And the same thing can be seen with data from CNR-ISAC, with the problem, however, that after the 15th of June, the instrument data are not cannot be taken in consideration due to the instrument problem. And here we can see the results collected for these 3 years, 2020 and 2021, at APL for tropospheric vertical column. Again, we can see the the red dots with the uncertainty bar, and the blue line representing the climatology. And in particular, we are interested in this graph below that shows the variation with respect of the expected values from the climatology. We can see the strong reduction of NO2 measured during the lockdown period, but even after the end of the restriction, we can see that the values we see that the values does not return to the expected value, are below for the entire 2020 and for the entire 2021. The same thing that for NO2 vertical column density. Again, we can see the strong reduction of minus 50% during the lockdown, and the data that are almost all below the expected value for the rest of the period that we taken into account. And at last, the data from the surface concentration measured in APL. Obviously, I cannot show you this kind of graph for the CNR ISAC because the instrument was dismounted on November, where we just reinstalled today. My colleagues are installing the instrument repaired in CNR ISAC. At last, to better visualize our results, I prepare you some monthly means that show the behavior of the NO2 trends during the 2020 and 2021. In red, we can see the CNR ISAC data, and in blue, the APL data for vertical column density, this first graph, the tropospheric total column density, and near surface concentration. Again, we are interested in this kind of graph that are the deviation with respect of the expected value. We can see the absolute minimum during April of 2020, and that the data does not reach the expected value even in 2021 after the end of the strong restriction. This can be caused by the fact that several people are working from home with smart working, and in particular many published employees that are not going to their usual place of work. To conclude this talk, I just show you the data collected by Pandora instrument of two Bakunin sites, APL and CNR ISAC. We see the lookup tables algorithm that allow us to compare the data affected by a bias in the time disposition. We see that we use different lookup table for work days and weekend to take into account the different vehicles mobility that characterize these two parts of the week. And we can see also that this kind of comparison allows us to take into account the different concentration of NO2 during the year. The lockdown period and in particular these 2 years offered us a unique opportunity to study the city's air quality under strong reduction of vehicle circulation, and our results are in good agreement with the results obtained by other researchers along the world in other European cities, and with the data that are reported in the European Air Quality Report of 2019 that say to us that 40% of the NO2 are due to traffic mobility, to urban traffic. Sorry, and this 40% is more or less the mean reduction that we measure during the lockdown period. And in particular, we can see that these results are confirmed in both APL and CNR-ISAC. We see the problem that affects the CNR instrument for the after the November 2020. And in particular, we compare the data from with the air quality station to see that if our data are consistent. And in conclusion, the study proven the effective capability of Bakunin to monitor the pollution in the urban environment. And these results are have been used, these results and this methodology, to publish a paper on 2020 that is Campanelli et al. And is reported in the references. Thank you for the attention.
Thank you, Gabriele. If you have any question, please feel free to raise the hand or to write them down in the chat. I think Raffaele has a question.
Okay.
Yes, thank you, Gabriele. Just curiosity, I see that the ARPA measurements has low standard deviation of the one acquired in the Bakunin. Do you know the reason?
Because we chose to use a consistent method to calculate the variation of our data. We use just the standard deviation for ARPA data, while in the Bakunin data are correlated with the measurement uncertainty. So we just not use the simply standard deviation, but we take into account all the uncertainty of the measurements. We have not information about the ARPA uncertainties data. So
Okay,
the shaded area is more pronounced for Bakunin data.
Okay, so thanks.
Thank you, Gabriele and Raffaele. Gabriele, I think we have a question on the chat. I don't know if you can see it.
Okay, sorry, I just shared the entire screen. If someone can read to me.
Okay, Jesus is asking, maybe I missed it, but did you calculate the correlation between wind intensity and NO2 concentration?
Okay, this is an interesting question. I calculate the correlation, but we here in Bakunin we decided to that the relation between NO2 and the wind data need to further studies. This because it is not it is quite simple to calculate the correlation. For example, here you can see that we have wind values that are below the reference data. And this period, for example, between March and April, correspond to a period in our measurements of not so strong reduction in NO2, but there are also periods in which we have, for example, wind stronger with respect of the average values that are not characterized by this kind of that are not characterized by strong reduction in NO2. This because it's quite complicated to put in relation the wind and the NO2 concentration, because we need to take into account that we are in a city. We are surrounded by high buildings. There are some quite complicated canyon effect on the wind, and also that a major role in the NO2 destruction is played also by the sun illumination. So we need also to collect data about the cloud coverage. So we just not adventured ourselves in this kind of speculation before a strong evidence. I hope the answer is satisfactory.
Thank you, Gabriele, and thank you, Jesus, for the question. Let's go on with Marco Restano. Thank you.
Thank you all.
Thanks a lot, and let me share the screen. Okay. So can you see my screen?
Yes.
Okay. So thanks a lot for having invited me to give this talk. I'm Marco Restano. I work at ESA ESRIN. The contract is the OPS, so Earth Observation Program Scientific Support, and I'm reporting to you the results obtained by the ESA Baltic Plus Sea Level project, which has been funded by ESA for 2 years and has ended a few months ago. The talk is about the monitoring of absolute sea level in the Baltic Sea. Okay. You can see my cursor, right? You can see the mouse pointer?
Yes, yes.
Okay, thanks. So why is sea level so important? Essentially from the latest conferences on climate change, was output have been broadcasted with televisions, and outcomes are pretty well known around. You know that sea level plays a cardinal role in climate change, and clear example of this is in the left side image, in which you see the city of Boston under the effect of a 3-meter sea level rise. So a few districts would result flooded. This is something, of course, that we don't want to see in the future, and that's why we need to study with radar altimeters mounted on these satellites, mostly from the Copernicus programs, so the Sentinels, the Sentinel-3, Sentinel-6, but also Cryosat, and also by reusing past missions. We want to estimate the sea level rise and to understand how the sea level is evolving and has evolved from the past to the present day, in order to indicate strategies to governments to reduce as much as possible this effect of climate change. As you can see on the right side, this is a typical figure that is presented at these conferences, and it's obtained by using several missions that have been operating from, for instance, in this case, 2002 to 2018. This means that we have to collect a lot of data, we have to intercalibrate the missions as we will see, and then in this case, for instance, you can see the black trend obtained by the ESA CCI, which is another project we followed in the past. And from these results, you can trace a trend line to understand how much the sea level is rising in this time period. As you will see in the next slides, the value is around 3.3 millimeter per year for this time period. Regarding the presentation I'm giving today, I want you to, first of all, I need to introduce some concepts for you to have these results clear. And that the first concept is the difference between absolute and relative sea level. Essentially, we talk about absolute sea level change when we consider changes in the height of the ocean as a result of the melting ice or the warming of the seas. But this tells only a part of the story. Because it's important, especially in relation to the previous figure we have seen before for the Boston City, what happens especially at the coasts, and so the role of land in interacting with the sea. Essentially, the land, because of several natural effects, but also because of human actions, can subside, for instance, so can move down and be more prone to be flooded, okay? And so in this case, when we look locally at the situation and we look at these effects, we talk about relative sea level. And it's mostly very important to understand this because for validating the data that we obtain with altimeters, so we need to consider tide gauge, which measure the sea level at the coast. So it can be here, can be in other areas. And of course, if the sea level is moving down, the result from the tide gauge will be wrong, and this will hamper the analysis because, of course, the sea level can be measured by the tide gauges, and so the figure that we have seen before can be measured also by a system mounted, for instance, by an harbor or at the coast. And so everything shall be controlled to make this analysis in order to provide to the community useful and trustable results. It's important for the specific case of the Baltic to keep into account this glacial isostatic adjustment, GIA. This is represents the ongoing movement of the land once burdened by the ice age glaciers. And to explain this, this seems to be something which is related to the past, when the ice covered, for instance, the surface of the poles, or also the surface of the northern Europe, in the glacial age. And essentially, when you have the melting of the ice, all these great mass of ice, which had the effect of moving down the land, once the ice melts, as for instance in sofa, you see down, you see the padding go down. When you move up, the padding of the sofa go up. And here you have the same thing. The land will move up once the ice is removed. And I will show you this in a video in a moment. Before, again, about the tide gauge I was discussing a minute ago in the previous slide, you have to consider that this is a system for local measurements, which has a reference, the tide gauge datum, and can be connected to a GPS system in order to provide a perfect collocation of the measurements. The GPS is typically referenced to another datum, which is the reference ellipsoid, typically used also in the altimeters, as we will see later. And the GPS is also useful to understand the vertical movement of the land over which it is located. This animation is pretty easy to be understood. Essentially, you will see several measurements taken of the sea level in various conditions, and this is to let you understand why it is so important to take into account the land measurement, and not only the polar cap melting, which is another factor that you will see in this video. So notch is the measurement, and you have a first value here. Then when you have, for instance, ice on land, of course the ice will modify the shape of the surface, but also the sea level will change, and you will obtain a second measurement. The weight of the ice will subside the land. We will have a third measurement. And from the melting of the ice, we have this effect, which is the post-glacial rebound, which is still happening today. And of course, at a very small rate, but we have to take into account, because the tide gauge, which is mounted here, would, if not, modify its value, calculating a wrong estimate. And then the polar ice cap melting, which is typical from climate conferences you have seen in these recent months, leading to the improvement, or better, to a greater sea level, augmented sea level at the coast. That's the thing we wanted to avoid, what we were observing for the Boston City. Now, in the previous figure, I showed you that the sea level trend was evaluated from the beginning of 2000, I think 2002, up to a few years ago. To make this, we need a series of altimeters mounted in several satellites. So, of course, we need to launch several missions, and as you can imagine, the technology varies between old missions and the newer ones. And so it's this implies that we have to take into account the possibility to use all these measurements, the older measurements and the newer ones, by intercalibrating the missions. And so at that point, we will be able to consider a unique time series as generated by a single satellite. And now we get to the project. So why the Baltic Sea? It's a very important region it's closely located to the North Pole. Essentially, there is a very good coverage from the satellites, a very good coverage from a network of tide gauges that provide validation data. And also the vertical land motion that you have seen in the previous animation is pretty defined and pretty present, pretty strong there. And it's due to the glacial isostatic adjustment I was discussing in the previous slide. And the altimeters, as you can see, this will be a bit better detailed in the presentation. They measure the sea level here. A radar footprint is included, is defined by the antenna. and then the processing leads to a certain resolution, as we will see. The measurements are typically of this shape, will be better detailed. And as we are in the open ocean, the measurements are clean. When the footprint results contaminated from the land presence, the contamination will be present also in the waveform that we process. And this is important because this means that the data have to be carefully selected, filtered out to provide to the retracker, which is the next processing level, the possibility to correctly estimate the sea level. Then the region is covered with ice, and so this is another point of challenge for the project. This means that we cannot use the baseline data provided, for instance, by Sentinel-3 or Cryosat-2, but we need to develop new strategies for coastal and for the investigation of altimetry waveforms in this complex scenario. Regarding the altimetry principle, to keep it very, very short, essentially we want to measure the sea surface height by subtracting two quantities. The first is the satellite altitude, and the altitude is controlled by GPS, SLR, and DORIS data, and it's known with an accuracy of 2 centimeters in the non-time critical products, which are released by ESA after 1 month after the ephemerides are well corrected. Then by taking the range, this is estimated from the waveform, from the blue waveforms you have seen before in the previous slide. If we take the range estimated and we take the altitude minus the range, we subtract this range. After having applied to the range all these corrections that you see here, so many because the waveform is contaminated by the propagation through the ionosphere, the atmosphere, and then there are several corrections and several other effects to be taken into account. Once this range is corrected, we make this subtraction and we obtain the sea surface height at a specific point with respect to the reference ellipsoid, which is in this case can be the WGS-84 or the Topex ellipsoid. Then there are two, as I said, we use old altimeters and new altimeters in this project, as you will see in the next slide. And essentially we have different technologies. I wanted to present something more about these two, LRM versus SAR, but it would have taken a few slides to be explained. So to avoid the running out of time, I prefer just to present this simple slide. The idea is that this is the area dictating the resolution of the instrument. And so in LRM mode, which means, for instance, the radars on board the ENVISAT missions or the AIRS missions or the SAR Altica mission, the resolution is dictated by the sea state, and so the resolution in the along track direction, which is the direction of flight of the radar, this one, is of a few kilometers. From 2 to 12 kilometers is the diameter here, and this is dictated by the roughness of the surface. So if the surface is flat, the return is very strong, and the surface is responds, for instance, in this way, it's very close to this way. If the surface is rougher, so if we have a typical ocean, the response will be of this kind. In case of sea ice, the response will be halfway in between. This is because in the Baltic Sea, we have 3 scenarios of interest: open ocean, sea ice, and then the leads, which are the cracks, the openings in the icy platforms, the ice shelves, if you want. Then this is the LRM mode, and these are 3 cases for the waveforms. And in every waveform, you have you transmit and you open the receiving window. You have noise. Then you have the leading edge here that reaches a certain maximum, and then you have a decay phase. And you can see this is valid for all the 3 shapes. Then this scenario dictates the backscattering process. But essentially, I want you to focus for the future on this leading edge here, because this is the part at which that we use to determine the range that you have seen in the previous equation. So the rest is something that it's part of the backscattering process, but it's something we don't use for the estimation of the range. Now we get to the SAR, which relates to these other 3 waveforms. And essentially, the SAR is a newer technique, not the newest, but it's on board Sentinel-3 and Cryosat-2. So it has been used in the last 10 years, let's say. And essentially, the pro here is that thanks to the Doppler processing used in this long track direction, we are able to reduce the resolution up to 300 meters in this direction, okay? And this is fixed no matter the scenario we are looking at. if the SAR, but the SAR only is applicable on the long track direction because it exploits the movement of the platform over a specific point. For this reason, the resolution in the other direction, the across track direction, is as in the LRM mode. So in the across track direction, you don't have any benefit from using the SAR. The ocean waveform is a bit different. You see that the decay is very fast for the power that you obtain after this after the maximum is reached. For the CIs, you have less power, and for the lead, you have a very coherent and very strong echo. Now, this was the background needed to understand what I'm telling you now. Is we can start discussing a bit the project, and essentially the Baltic Sea project aimed at measuring absolute sea level trend from May 1995 to May 2019 in the Baltic Sea by producing, through the processing of many altimetry missions, a regional monthly gridded data through the adoption of a dedicated SAR altimetry processing and LRM processing, also adopting newly developed geophysical corrections, those that you have seen have to be applied on the range value. Then, once this data set has been produced, first it was a long track for each mission, then it has been combined to produce a gridded data set, and then it has been used to make analysis on the variability, so the trends millimeter per year as the first figure you have seen in the various basins, and also to evaluate the role of the winds and the relation to the North Atlantic Oscillation, which is a phenomenon I will briefly describe later. Of course, this is useful for understanding better the situation in the Baltic, produce a regional product that can be used by different communities, and support climate change studies, as it's clear, I think, from the first slides discussed. And the processing strategies essentially starts from here, from the acquiring the waveform. So I want to spend time on this because it is just the waveform as acquired by the altimeter. Then, as I showed you, that we have several possibilities of echo shapes for the different scenarios, we will classify the waveform using a neural network classificator to understand when waveforms are usable because they respect the shapes that we expect. And after that, the waveform is accepted. And then we continue the processing by applying a retracker, which is the processing step allowing us to extract the R value, the range value, the one we have seen here, the R value here, from these waveforms. So once the range is estimated, we have to apply all the different corrections that we have discussed here, all these different corrections. In particular, one of them, the sea state, is quite critical and has been developed in the project in association with the tracker AILS Plus, which has been developed for especially for the SAR mode. So once this is clear, so classification, retracking, adoption and production of the right corrections, we obtain mission ranges from all these satellite altimeters, and we can start by making discussions on the estimation of the trends. Essentially, we have several data sets which are along track data sets. As you can see, this is a piece of the orbit you can imagine on ground. And we will have many of them, and we combine all of them in a cross-calibrated product in order to combine the whole information from the whole mission and to allow this investigation over the indicated time period of the project. Important to understand that apart from the resolutions that have been discussed here, altimetry products are given in output in this way. So you have a track, and then you have estimates with a certain interval separating one another. And this is dictated by the so-called posting rate. So if it's 20 Hz, you have a separation of 300 meters. In the past, it was used also for LRM mission 1 Hz, which means 7 kilometers. And so this is dictated, of course, by the capability of using a newer system or an older system. Just to point out one thing, the benefit here is that with SAR having a higher resolution, we can get closer to the coast, way closer to the coast, up to, for instance, 2 kilometers to the coast, having valid data. with the LRM, as the footprint is 2 kilometers at least, or even 5 kilometers in the long track direction, the footprint gets contaminated before the coast, and so we can get good results, but around 5 kilometers, 6 kilometers. Now, to move forward and to explain exactly each box here highlighted, let me tell you something about the classification in brief. Essentially, as I told you, as I was anticipating, we use neural network algorithms, and essentially every time we use this approach, you have a training phase and then a validation phase. The training phase, actually, you take a part of the data set devoted just for the training, and you train the network, providing all these important parameters characterizing the waveform. So the leading edge, the trailing edge, the maximum power, and some other parameters. And you train the neural network using these characteristic parameters of the waveform. Then you have trained your neural network, and you move to the validation phase. So you take the data set that you haven't used so far, and you check if the network is capable of identifying measurements over the ocean, like those you see here, and measurements over the leads or CIs, which are those over the platforms. And so you see that all the others which have a shape which is distorted or severely contaminated are filtered out and indicated as red in this figure here. So this is a classification unsupervised and allows you to filter out the data that you consider not valid for your analysis. Then the retracking phase is the way of extracting, again, the R value from these waveforms that you have seen here. Now, this is the process goes with the application of a model representing for the ocean a sea state, for instance. We test several models, and the best fitting one is considered the model representative for the sea we are looking at. Now, the point is that with the contamination of the waveform, for instance, this is a clean ocean waveform, as you have seen before. For the coast, you can see that there are spikes, there is some contamination. So instead of having a model covering the whole waveform, you see here the red part stops here. We have the so-called sub-waveform retrackers, which just consider the portion of the waveform which is useful to estimate the range value. And so you see that the red part of the model matching the waveform is actually stopped after the leading edge, except for the leads. This is the LRM, and this is again the SAR case. Important to point out that the range is obtained by retrieving the midpoint here in green. And so it's perfectly doable by applying this model. And this is the ALS plus is well known because instead of considering the full waveform again, it considers just this piece, and it's not influenced by eventual presence of contamination. So this is the advancement brought by the project in terms of retracking. And the next one is that the project has also estimated a specific sea state bias from the retracker output. And so this is another very important output of the project. Now that everything I think is clear, we have selected correct waveforms. We have retracted the waveform obtaining the range value. We have also estimated the sea state bias. What we have to do is to include all the other corrections from known references to estimate what we were looking at. So the H here, which is the sea surface height. And so we make this by subtracting again the altitude of the orbit, that was S before, minus the corrected range from all these effects. And this is something that leads us to say that we have reprocessed all the emissions, LRM and SAR, applying these approaches, this classification of the waveforms, this retracking, this sea state bias retrieval, to obtain a new data set specific for the Baltic, so which can work in presence of sea ice, which can work in presence of contamination of the coast. Now that we have all these data sets together, every data set will show tracks of this kind, okay? And the sea surface height can be determined for each track by following the equation that we have seen. Point by point, again, the posting rate will be, for instance, 20 Hertz with measurements estimates every 300 meters. Of course, when we have several missions together, we can intercalibrate them, so compensate for the biases, understanding if the instrumental errors are applying, for instance, some bias that we have to compensate or not. And then we obtain this trend in which it goes like we have a single mission, but actually we are using several missions, like from topics from JSON tree. Now, from this, we can make an estimation of the trend and obtain a value, which is the 3.36 millimeter per year, telling you the sea level rise in this time period. This is from an old project. It was just to give you an overview. But I want to underline that we will obtain this estimation, so millimeter per year, for the sub-basin we are studying, so for the Baltic Sea. Of course, it's useful to include many missions because this allows us to cover more space than the one covered by a single mission. And then, of course, the time sampling improves because we are using missions like Envisat, for instance, which have a repeat cycle of 30 days, 35 days, sorry, which means that I get back on the same point after 35 days, whereas with JSONs, I get back on the same point after 10 days. And so by mixing different missions, intercalibrating them, I improve the space-time sampling of the sea surface heights. And then from this along track data, like those here, single tracks, to a gridded product, the step is the following. So you define an unstructured triangular grid, you combine all the tracks on it, and you interpolate the results on the grid points. And so what you obtain is something like, if you zoom in, you obtain a grid of this that looks like in this figure, what you see in this figure, and this is the step of gridding. Then, as clear, we cannot fully rely on altimeters yet, but we need to verify our results using a validation data. And now you understand why I reported in the first slide a discussion on the tide gauges and on the relative sea level and on the effect of subsidence, no? In which we had the land moving up because of the post-glacial rebound. So essentially, we have tide gauges when you see the dots here, and you will see dots in the next figures where tide gauges are located. So please keep this in mind, because from now on you will see results showing dots indicating the position of the tide gauges. Of course, as you may imagine, from both tide gauges and altimeters, we will have through the years a time series of measurements of sea surface height. In this case, you see the sea level anomaly, which is the sea surface height minus the mean sea surface, which is a reference. So you see an anomaly is something which drifts from an average behavior, okay? But it's exactly the same. It's just another way to see the sea surface height. So we will have a time series from the data that we can have from the tide gauge, and a time series from each grid point over which we have interpolated our altimetry data from the Baltic plus CL processing. Now, it's clear that the datum, the tide gauge datum, and the datum of the altimeter, the reference ellipsoid, are different, and so they need to be homogenized, and this can be done in various ways. Then we need to, if the tide gauge is located here, you see my mouse pointer, and it will be like this tide gauge, same position. We cannot take for the validation the data acquired everywhere, but we take just the data close to the tide gauge. And a good radius, a good area is to consider 20 kilometers away. Is to consider all the measurements taken within 20 kilometers from every tide gauge. And then another thing is that we have to compensate the tide gauges for the post-glacial rebound, so the GIA, as I told you before. And then we can compare the two measurements. Once, for instance, we have demined both time series to avoid the difference, the impact of the different datum in both. Again, I like to point out that with altimeters we measure the absolute sea level, whereas with the tide gauges we measure the relative sea level. Okay, now the typical validation analysis needs to estimate two quantities: the Pearson correlation coefficient and the error. And as you can see, the Pearson correlation coefficient is very good. Can reach also 100% in some regions, which are probably less complicated to be managed by the altimeter point of view. Of course, you have to imagine that the classification can be misleaded sometime, or that the geographical corrections can be very good, for instance, here, and for some reason they are not very precise in this region. So there are a huge number of reasons justifying a contaminated waveform, a contaminated estimate. But you see here the results are indeed very, very good, because the correlation coefficient is mostly above 0.7. And also the RMSE, so the root mean squared error, is very low in the region, apart from a few tight gauges. So I would say very good results. Then the analysis of the sea level, so the millimeter per year I was telling you before that we have seen in the previous figure, like this one. Now it's done with the Baltic plus seal data. And so we study the trends, which means that to estimate a trend, so millimeter per year for each grid point, which justifies this color in the region, again, the circles are related to the gauges for comparison and for validation. We take the time series and we fit a model composed by a bias, a linear trend, and a monthly variable and an error. And then the fitting is made, the trend is retrieved, and it's placed as a color in this figure. And so you see that there is a clear variation in the area. There are areas in which there are 6 millimeters per year of trend of increase in the sea level rise during the time in which we made the analysis, so from 95 to 2019, and other areas in which the trend is significantly lower. The uncertainties are way lower in all the region, and this is very good, because it means that the statistical analysis is correct. Then let me show you how we can say more about the trends in relation to the winds by splitting the analysis for winter months, so December, January, and February, and summer trends, which means June, July, and August. For the summer trends, you see that the trends are quite constant. There is the same color, so the variation millimeter per year is very small, okay, I would say, if not absent. In the other case, for the winter trends, you see a significant difference in the trends. So there is something happening which modifying the millimeter per year, the trends in this area, the Bay of Bothnia, and in the Danish Strait, and also in the other areas. So, and this is verified also by the tide gauges, because you see the colors are pretty well matching what we see here. And again, this is a comparison, a validation. Now, to study what's happening, we can adopt this approach, which is through the empirical orthogonal functions, which are well suited to analyze time series in which we want to identify spatial structures and temporal evolution without any a priori information. And so we take this analysis, and it leads us to two functions. The first one shows a clear pattern, a clear uniform pattern, and the other one shows a pattern which varies in the basin in a way which is very similar to the one we have seen here. Okay, so to relate this to the effects of the winds, we need to correlate and to estimate the accompanying principal components to the zonal and to the meridional wind components. So we relate the results to the wind maps in the same time period. And essentially, as you can see, the two zonal components, the two wind components mean the following. Essentially, the zonal component is the wind component in this direction, so west-east, while the meridional component is the wind component, or is the component of the wind blowing from south to north. Okay. So when you correlate with both components of the wind, you see that there is a very good correlation for the first uniform orthogonal function on the meridional component, and this was expected and known from another work. Whereas for this other part of from the second function, explaining the variance in the basin and showing this variation in the variance, which is related to, again, what we have seen here, you see that the results are very well correlated, correlation, so red, close to 1, with the meridional component of the wind. And this indicates a possible influence of the meridional wind in shaping the trend in this area. So this variation, millimeter per year, is different in these areas, because of the presence of the winds, which blows in this direction, this meridional direction. Another thing that can be said is the relation with the North Atlantic Oscillation, which is a winter phenomenon over the Atlantic Ocean of fluctuation between the difference in atmospheric pressure between two regions, the Iceland region and the Azores region. And as you can see, if we consider the impact in the Bay of Bothnia, which is this area here, you can see that we have from the data, the North Atlantic Oscillation has this variation, okay? If we consider the sea level anomaly that we estimated with the products of the Baltic Sea products, you see that there is a very good correlation with this North Atlantic Oscillation. And this means that we are able also to follow and to reproduce with the products this other phenomenon, which is dominant in winter. This explains a bit the project. So the conclusion is that the sea level has been studied and analyzed in the time period from 1995 to 2019. Sorry, reprocessing has been made, including classification, improved retracking strategies, improved assisted bias correction, which allowed having much more data in coastal areas or in ice-covered regions. And this is very important. Then the validation has been made with the corrected tide gauges data. Trends have been correlated. The correlation is very good. And then the results have been studied in relation to wind patterns and also, sorry, just a second, I lost. Okay. Has been read to wind patterns and also to the North Atlantic Oscillation Index in the winter. Regarding my role in this project, as you know, is the project we are following. Essentially, I review all the project deliverables, meaning that I consider the datasets produced, the documents produced. I review all of them to suggest modifications, highlight errors in the products, errors in the waveforms. And then we provide reviews to improve the document, to improve the data sets, and unlock the payment milestones. Then I supported the preparation of codes and handbook for the users, which is associated with this data set that has been the output, the main output of the project. And then I performed an independent validation using not the ESA Sentinel-3 official products, but those made available in another repository, which is the ESA Salvatore for Sentinel-3. Processing facilities, which is a facility that allows users to process online and on demand Sentinel-3 data, applying specific processing options not available in the official Sentinel-3 processing chain. There we had these Samosa Plus and Plus retrackers, which are considered the best retrackers for the coastal areas, for the ocean coastal areas, and also for the ice regions. And we have compared this retracker with the ELS Plus R. I made all the study. This has been presented at a conference, and demonstrating that the ELS Plus R developed in the project is also performing very well in line with Samosa, if not even better in some regions. And that's all. Thanks.
Thank you, Marco. If you have any question, please feel free to raise the hand or to write them down in the chat. No question? Okay, let's now pass to the fourth and last part of this event, which will be dedicated to interns presentations. I will now give the floor to Massimo Valeri, introducing Marianne Bargiotti from Bologna University. Thank you.
Thank you, Viviana. Thank you, everybody, to be here. I'm Massimo Valeri, and I'm the tutor of Marianne for her internship in CERCO. I'll briefly introduce her and the activity that she performed during the internship. Marianne is a student of the second-level master of the University of Bologna. This is the first edition of this master called the SPICES, which stands for Space Mission Science, Design and Application. CERCO and even Redlab supported this master by hosting Marianne for her 4-month stage that will finish by the end of the year. The internship activity has been performed in the frame of the Airwave project, a project funded by UMESAT, in which CERCO works together with the ISAC CNR in Bologna. Here is the connection with Bologna and the scientific environment present in this city. The objective of this internship is to perform further validation of the Airwave SLSTR total column water vapor products. A new dataset has been recently produced, and this is longer than the one that we used in the previous version of the validation. Marianne performed a validation exercise on this new dataset with respect to another reference satellite-borne dataset. Thank you again. So I leave the ball to Marianne.
Hello, you hear me?
Yes.
Okay. Yeah. Hi. So, as introduced by Massimo, I'm performing this validation and comparison satellite water vapor dataset and atmosphere. Sorry. Okay. This internship is within the framework of the Dataset project in order to extend the Airwave algorithm to SLSTR in order to produce new operative Sentinel-3 total color water vapor level 2 product, exploiting the unique capability of Airwave to retrieve the total color water vapor over a water surface on water surface in a cloud-free condition using the TIR channel, the thermal infrared channels, so working both day and night time. Very briefly about the history of the algorithm. The retrieval of the total color water vapor for in the night condition and cloud-free scenario on water scene stems from the TIR measurements from the long track scanning radiometer series. From the 4 measured brightness temperature at 10.8 micrometers and 12 micrometers in both of the views, was possible to obtain to retrieve the total color water vapor. This is the reference to the very first version of the Airwave algorithm. Anyway, as the Dataset project is working on the Sentinel-3 satellite, very briefly about the new radiometer on which Airwave is working on. The SLSTR. Sentinel-3 this is the European Earth Observation Satellite mission within the Copernicus project for ocean, land, atmospheric emergency security monitoring. And an STR is the radiometer together with OLC as well and MWR. Sentinel-3 has been launched on February 2016 and Sentinel-3B on 2018. The LSTR fundamentally is providing an accurate and a wider data set in order to provide a reference for other sea surface temperature mission for a satellite. Together with the SST, also the instruments is providing sea and land ice temperature, atmospheric aerosol cloud properties, and fire monitoring. With the main characteristic here depicted. What is the main difference from what has been done before from the ATSR measurement? So the main difference that we encounter obviously is first of all is the viewing geometry that is shifting from nadir forward from the ATSR series to a nadir backward, together with the very different with for the SLSTR. Together and also, but not related to exactly to this analysis on the visible spatial resolution. So fundamentally, what we are dealing with, most important thing to deal with is the viewing geometry and the spectral response function of different instruments. So main aspect that we're dealing with in this slide, I summarize the main aspect that has been evaluated or implemented within this new version of the code. First of all, as said, that the viewing geometry is shifting with respect to the previous one, and this change of the viewing geometry, no effects of limitation from this change has been observed. Together with this, there are the spectral response function for the parameter computation. Spectral response function is crucial, and the computation of the parameters used for the retrieval. And as these parameters represent the atmospheric surface scenario, and they are pre-calculated offline. That's my pointer. Yeah, it's calculated offline for 72 different scenarios using the atmospheric profiles from ISG2 climatological database. More than this, the coefficient and then obtained internally to the level 2 processor by interpolating along tri-dimension, time, latitude, and viewing angle, using an interpolating latitudes that is varying with season. More than this, we have the uncertainty assessment with accurate characterization of any type, two types of uncertainty, type A and type B, and then are further reported within the last year direct to products. More than this, the prototyping and the version of the code, so any updates and change to the code has been tracked using versioning software and a GitLab HumanSat repository. The new data set available. The frame of the HumanSat project, the Airwave team already performed a first validation using 4 months from 2018, January, April, July, and October. More recently, that is the main subject of this main focus of this internship. Longer 12 months data set has been made available from May 2020 to April 2021. And within this internship, I validated this new data set with respect to the total column of the vapor of the spatial sensor microwave imager. This is SMIS. So, validation strategy. First of all, the Airwave product has been regraded according to the spatial resolution of the SMI. And we have calculated daily fields of day and night separately and computed daily difference with respect to the SSMI. To the column water vapor obviously. We use the SSMI F-17 satellite production as the F-17 satellite is properly covering the entire SLSTR mission period, and the ascending node as that's already more stable in comparison with other SSMI satellites. For the analysis has been used both the Bayesian and a classic cloud mask, and are to filter out SLSTR observation trigger as cloudy. And more than this, another flag that has been used as a liquid water content on SSMI product as a proxy of presence of clouds. So any coincidence with the level with the liquid water content flag bigger than 0 has been excluded from the analysis. So let's go into the sum of the scatter plot. On the first row, we can observe the 2008 months available that has been already validated, and in the second row, same months from 2020-21 can be observed. In general, we can observe a pretty good agreement with a level correlation and pretty similar form of lobe. Particularly, we can observe this all this both the first row and the second row has been treated in this one in the Bayesian mask. We can observe for January the presence as highlighted with the red curve here of this artifacts, mostly due to that is still present even to a lesser extent even and that in a more recent data set to the less than perfect cloud filtering. More than this, the lobe that has been observed in July 2008 is still evident even in July 2021. So, more than this, latitudinal distribution, what can be observed? The most striking point that can be observed is the unfair, that's general agreement between the 2018 and 2021, with the generic that agreement referring to summer hemisphere that is particularly evident in July 2018, slightly less in 2020-21. For this, moreover, I have performed also seasonal comparison, subdividing the one-year data set in 4 sets of 3 months each, and comparing the results from a Bayesian mask with a classical mask. So we have December, January, February, March, April, May, June, July, August, September, October, November. What can we see? Again, Bayesian mask offers a pretty pretty high level of correlation and an overall bias that is for sure less than the one of the classical mask. Anyway, to be noticed, there are still presence of these artifacts that are reproduced both with the Bayesian mask and with the classical mask in this case for June, July, August, that are referred to imperfect cloud filter. Anyway, higher bias characterizing the classical cloud mask and a lower number of entries in the classical cloud mask. So in here I have taken 3 different months that are June, October, and January from the new data set in order to highlight some points. June, as beginning of the summer northern atmosphere, is presenting as shown before an initial, and this is more evident in June, in July and August. Bad agreement for mid-latitude, mid-higher latitude, and in October, fairly good agreement for the latitudinal distribution between the latitudinal distribution and high level of correlation, and bias that is for sure less for the Bayesian mask. To be noticed, still the presence of this cloud filtering. And then third is January 2021. Again, still the presence of this imperfect cloud filtering, and this start to be evident, the doubling of the peak that is most likely referred to the ITCZ trend. So coming to the full data set result, considering both the results from Bayesian and the classical cloud mask on the left-hand side, the result on the upper side, the Bayesian, and the lower part, the classical mask, the classical cloud filtering mask, and on the right-hand side instead the summarizing table of all the different for all the different months. For the Bayesian cloud mask, the total bias evaluated is -2.34. That is fairly better than the 2.84 is related to the classical cloud mask. All this leading to the preliminary conclusion for this validation. This result is for this new data set comprising of full air confirms the result that has been obtained at the previous validation exercise with a generally good agreement between Airwave LSLSTR product and an SSMI1 and a mean bias that is -2.34. That is pretty comparable with the bias of -238 as from the first validation in 2018. As observed, a larger dry bias with respect to SSMI in some atmosphere, and with the worst agreement in the August and northern hemisphere. Totally, for sure, better agreement using a Bayesian cloud mask with respect to external one. Next one. That's all.
Thank you, Marianne and Massimo. If you have any question, feel free to raise the hand or write them down in the chat. Raffaele, you have a question?
Yes. Thank you, Marianne, for the presentation. I have a question about the cloud mask. You are using the cloud mask on the Airwave dataset, or also on both datasets, SSMI and Airwave dataset?
This is for the Airwave one. Yeah, I mean, they are working on both, obviously, but the SSMI is, the cloud masking is particularly efficient now for the Airwave. ES is working on the TIR channel, while the microwave channels are less sensitive, let's say, to this kind of problem. That is anyway The Bayesian mask both and the classic mask are working for the TIR channel mostly because this cloud masking is affected more the infrared channels.
Thank you, Raffaele, and thank you, Marianne. Following, we now have Adriana Castriotta introducing Federico Cianciotta from Tor Vergata University. Thank you.
Hello, good evening, everyone. Well, I'm pleased to introduce Federico Cianciotta, which is a student for the master degree in physics and complex systems and big data in the University of Rome Tor Vergata. Can you confirm you are hearing me? Because I just don't see.
Yes,
any.
yes.
Okay. Okay.
Yes.
Okay, so Federico has started to work to this project, which aims is to study how optimize the data storage cost of Onda Dias. This project actually started in 2019 by Gaia Cipolletta, the other tutor of this training, and now it is the argument of the master thesis of Federico, which successfully completed the training in Cerco last week, and is going to discuss his thesis at the end of this week. Just for a little introduction, the Onda Dias is a data and information access system, which is a platform enabling users to host data and to build their application on the cloud. At the time of writing, Onda collected more than 36 petabytes of volume downloaded by the users, and the study done by Federico and Gaia so far is a proof of concept it's machine learning for minimizing the cost and automate the monitoring of data dissemination activities. This is going to be also a demonstration that Cerco, in collaboration with OVH cloud provider, is able to apply and operate the most advanced and state-of-art technologies in terms of data science. Now I leave the floor to Federico, that will show more details of the results.
Thank you, Adriana. Hi, everyone. Share my. Okay. Do you see the presentation?
Yes.
Okay. So my name is Federico Cianciotta, and my work is entitled Artificial Intelligence for Optimization of the Dias Onda Storage. During this presentation, I will talk you about the objectives and the content of this work. I will give you a description of the project, and finally, I will show you the results obtained. The objective of the study is the analysis and application of machine learning techniques for the identification of download patterns in user activity on the Onda service operated by Cerco. This is done using AI, developing a proof of concept that then goes to support the decision process on the storage optimization. So let's start talking about the data used. The data relate to the Copernicus program. Copernicus is the European Union's Earth observation program, which monitors our planet and its environment. And it is directed by the European Commission in partnership with the European Space Agency. Copernicus information services are based on data from 7 satellites known as Sentinels. The Data Hub services provide the full set of Earth observation products of Copernicus missions to users, following the high-level diagram represented here. So the DUS data access system retrieves products and publishes them online on a series of dissemination points known as hubs. Accessing these hubs, users can explore the data collections and clearly can download products. Serco is involved also in data information and access services with Onda. This Onda is a cloud-based platform developed to facilitate the access to Copernicus data and information. In Dia's Onda catalog, there are Sentinel's data and also Copernicus services information and other very high resolution data. So here we can see that there are more than 36 petabytes of Earth observation data in Onda, which are about 60 million products. New products are added to the online archive, the object storage. And when some time passes according to rolling policies, these products are moved to the cloud archive, where users can still download them, but with time delay. In this diagram, we see the high-level scenario. Users download products from the Onda catalog. The download statistics are reported into a data warehouse on which a machine learning algorithm will then be used to detect patterns in users' activity for monitoring purposes. All of this is reported into a dashboard so that the service manager can review the results and make decisions about the allocation of storage. So the work is divided into two different parts. The first one is the application of an unsupervised method, a clustering algorithm, because we want to group data into different clusters. The main idea is that data into different clusters are different one from each other, but data into the same cluster are similar one to each other. In the second part, we will use a classification algorithm, and we will train a neural network in order to classify data with the labels generated in the first part of the work with the clustering algorithm. So with the pre-trained neural network, we will be able to classify new data. Here we can see an example. So we have the dataset with different features. We apply the clustering algorithm, and so we add labels to the dataset, and we can train a neural network on this dataset, and so we can classify new instances, adding labels to this data. So the feature used into the dataset are the age from the publication date, so the difference between download date and publication date of the products. Age from sensing date, so the difference between download date and sensing date, but also mission type and size of the products, and the footprint of the products, so the geographical area of them. The problem is how to use this feature into the dataset, because the footprint is represent a geographical area. So in order to do this, we used an autoencoder. An autoencoder is a particular kind of neural network. Its task is to reconstruct the input, but its main characteristic is the bottleneck shape, so that in the middle of the autoencoder, we have a code. There is a vector that encode the input. So with our autoencoder, we have a code with 4 values that are used as 4 new features into the dataset. So here we can see 7 examples of products with the footprint and the reconstructed footprint by the autoencoder. So now we have the dataset with all the features, and we can apply the clustering method. The method used is the k-means. In k-means, it is necessary to select one parameter, the k. To do this, the elbow method is used, which consists in plotting the distance between the points and the centroid of their cluster for each value of k. The optimal value of k will be that for which there will be no more gain in increasing k. But we can see here that there is no elbow in this figure. So we used also the silhouette method. The silhouette value is a measure of how similar an object is to its own cluster compared to other clusters. The silhouette ranges from -1 to +1, where a high value indicates that the object is well matched to its own cluster and poorly matched to other clusters. The value is calculated as the difference between B and A, where A is the mean distance between the point and all other data points in the same cluster, while B is the smallest mean distance between the point and all points in any other cluster. Here is reported the average value on all points of the silhouette score for different values of K, and we can see that that 20 is the best value of K. So we perform clustering with, we perform K-means with K equal to 20. So here we can see clustering results. It can be seen how these two clusters, 1 and 16, represents products found in Europe. You can also see other differences between these two clusters. For example, in the feature age, we see that data of cluster 1 are downloaded as soon as they are put online here in the first days, while data of cluster 16 are downloaded with an age between 100 and 300 of days. Here we can see other two clusters, 4 and 6, where the products are from the east area of Asia, as well as differences in various features. This figure shows the percentages of data in each cluster. So we see that there are 20 clusters. In blue, there are the counts, and in yellow, there are the products volumes. So we can see that there are differences between percentages in counts or in volume. For the last part of the work, a neural network is trained on the dataset, where labels are added to each data. We can see that after 30 epochs of training, the neural network reaches about 98% of accuracy. Here on the right, the confusion matrix is reported, which has the labels predicted by the neural network on the x-axis, while the correct labels on the y-axis are reported. So you can see how each individual cluster performs the classification. Clearly, after training the neural network, it can be used to classify new data and assign them label. So a cluster. Thank you.
Thank you, Adriana and Federico. If you have any question, please feel free to raise the hand or to write them down in the chat. No question? I am now pleased to introduce Lorenzo Trenchi, introducing Nicola Plutino from Tor Vergata University. Thank you.
Good evening, everyone. Lorenzo, are you here?
Sorry, I was not able to find the button to unmute me. Okay, so are we starting? Can you hear me?
Yes.
Okay. So in this presentation, we will show the results, the preliminary results of this master thesis from Nicola with the internship in Serco. And we will focus on the role of interplanetary shocks and coronal mass ejections and their role in generating geomagnetic storms. So Nicola, can you go to the next slide? So the context of this master is in the solar wind geomagnetic field interactions, and everything starts with the solar wind. Here I put the description from Wikipedia, and this says that it is a flow of charged particles, which means it is composed by a plasma where positive and negative particles are separated each other differently from a neutral gas. And so also magnetic and electric field plays a role. They are very energetic. Here in the plots below, some of the more relevant parameters, starting from magnetic field magnitude, which is much weaker than the field that we measure on the Earth. In this case, it is measured in nanotesla, so it is 10 to the power of -9 Tesla. Then the second panel shows the bulk flow speed, which is instead very, very fast compared to the speed we are used on the Earth. It is measured in kilometers per second. There is quite a variation of this parameter during the months that I graphed here. This graph starts from 1st of August 2021 up to the end of November. And it is the data are measured by ACE spacecraft, which is flying in the Lagrangian point L1 in front of the Earth. So it is a good proxy of what of how the solar wind is impacting the Earth. And the peak that we can see here at more than 700 kilometers per second after the 1st of November will be the event of which Nicola will talk in the remaining part of the presentation. And the last parameter in this graph is the ion density. The solar wind plasma is very, very tenuous. So the number of particles per cubic centimeters is only in the range of 10 to 20. So Nicola, if you can go to the next slide. So this is a cross-section of the Earth's magnetosphere. In the vertical orientation is the north-south direction, while the direction on the left of the figure is the sunward direction. So it is a vertical cross. The solar wind reaches the Earth orbit being supersonic and superalphenic, which means that it is faster than any wave propagation in the plasma itself. And so in order to be slowed down, the interaction with the geomagnetic field creates this bow shock. Shown here is a paraboloid with a mean distance from the Earth around 12 to 15 Earth radii. So the small circle at the center of the figure is the Earth, actually. And downstream from the bow shock, the magnetosheet plasma is subalphenic and subsonic, and so it is slowed down. And the second boundary formed in the interaction of solar wind with geomagnetic field lines is the magnetopause, which roughly separates the solar wind plasma outside, so on the left of it, from the geomagnetic field lines inside of it. As we will see in the next figure and then in the presentation, so again, the same picture on the right, the motion of solar wind is transferred in the magnetosheet and then also in the ionosphere, which is a very thin layer around surrounding the Earth at altitudes starting from 70 kilometers up to a few hundreds of kilometers, so very, very close to the Earth in this figure. And the main mechanism from which the plasma motion, the solar wind plasma motion is transferred down to the ionosphere is the magnetic tension, which in the MHD equation, which stands for magnetohydrodynamic equation, is called Hall term. It is given here by this expression. And roughly speaking, this tells us that whenever is present a field line across a plasma, two different plasma layers, in this case, the top plasma layer can be considered the magnetosheet plasma, especially in these polar regions, so up and down with respect to the Earth. And the bottom plasma layer in green is instead the ionospheric plasma. Any curvature in the magnetic field lines is able to transfer the motion from one plasma layer to the other. In addition to the motion, this interaction creates also currents. One of the main ones what we will listen in this presentation is the field aligned currents, which is moving along the geomagnetic field lines. This presentation will focus on the auroral regions, which are these small, Nicola, if you can go on the Earth with your cursor, you can indicate, now in the previous slide, you can indicate, yeah, at the top, yeah, these small parts on the Earth are the auroral regions where the plasma in the ionosphere is coupled with the one in the magnetosheet. And so in these regions, the field lines are mostly vertical with respect to the Earth's surface. The field aligned currents so are perpendicular to the Earth's surface and are called field aligned currents. And now if you move to the next slide. Yeah, so on the left, we see the configuration of field aligned currents from various local time sectors. So at the top of the figure on the left, it is written 12, which stands for noon. So it is the direction pointing toward the sun. On the right, the sunrise, and on the left, sunset, while the bottom part of the figure is the night side region. So in the opposite direction with respect to the sun. And this is the main configuration of field aligned currents. And in addition to this, aligned with the field lines are present also horizontal currents, so parallel to the Earth's surface, which are instead represented by the scheme on the right. And this is the main context. In the following part of the presentation, we will see the observation from several spacecraft at different distances from the sun, trying to understand which is the main driver in the solar wind, and then what happens in the Earth ionosphere according to the coronal mass ejections observed in the first days of November this year. Now I leave you, Nicola.
Thanks, Lorenzo. Okay, so as Lorenzo already described, Earth was hit by a geomagnetic storm at the beginning of November 2021. And this was caused by multiple coronal mass ejections by the sun. In particular, here you can see on the right a picture, a movie taken by Soho coronagraph with the biggest of these CMEs on the 2nd of November 2021. And starting from this point, we are going to look at data from different satellites and understand when interplanetary shocks happened and how the geomagnetic storm developed. Let's start with satellite positions. Here you can see ACE satellite and WIND satellite, which are NASA programs, and these two satellites orbits around the L1 point. This will be the satellite closest to the sun, from which we are getting data. And then we can see Themis C, which has been recently moved into an orbit around the moon. The satellite MMS-1 has a black square on the picture. And this is essentially one of 4 satellites investigating Earth magnetosphere. While at the center of this plot, in the origin, you can see a small light blue point, which stands for the 3 swarm satellites, Alpha, Bravo, and Charlie. And these satellites are devoted to the study of the Earth ionosphere and the coupling between the ionosphere and the magnetosphere. Since on the left it is only a little point, on the right reported a detailed orbit of Swarm A and Swarm B, since Swarm C is flying very close to Swarm A, so it would have been useless to show it on the graph. Let's start from the the one of this satellite which is closest to the sun. In particular, you can see ACE. On the right, on the left, you can see the magnetic field intensity and its components. And you can clearly see that at a certain point, at the end of November the 3rd, there's a huge jump in the magnetic field intensity. And this same behavior can be observed also within plasma parameters such as the plasma density and plasma temperature, which you can see on the right. And this red line on each of these plots stands for the happening of the interplanetary shock. If we get closer to the Earth, just a little bit, we can see data from wind satellite. And as you can observe, the behavior is essentially the same since we moved just a little bit. They are both orbiting the L1 point. Here you can also appreciate the different wind velocity components. Look closer at the starting point of this interplanetary shock. We can observe that the shock reached, of course, first ACE at 1920 of the 3rd of November, and then at 1935 it reached the wind. Getting more close to the Earth, we have Themis Sea observations. In particular, we have again 2 days data plot centered at the whole geomagnetic storm, the whole event. But in addition, you can see on the picture on the right, which is plasma parameters data, that we also have spectrograms. And the spectrograms make obvious that the shock happened since there is a huge change in the plasma composition. It's like looking at 2 different plasmas here. I don't know if you can see the pointer, but right here, it's like we are looking on the left and on the right of 2 different plasmas. At this point, we have data from wind from Themis Sea, which are about 140 radius of the Earth distant. So it is possible to give an approximation of this CME speed. You can read it is about 1,400 kilometers per second. So very fast CME. If we get even closer to the Earth, we can observe data from MMS1. We have the same kind of behavior already observed in other satellites, such as the jump in the total magnetic field intensity. But this time, we can see something particular, since MMS accounts for the magnetospheric response. It is in Earth magnetosphere. And we can see that because of the shock, there is a passage from a magnetosheet behavior to a solar wind behavior, which is marked by this dashed line on the picture. If we get on ground magnetometers, so we refer to indexes of geomagnetic activity, we can clearly observe when the event started and how long it lasted. In particular, we have the DST index, which is a measure of the equatorial ring current. And this is on the top side of this plot. While on the bottom, you can see auroral electrojet indexes, which accounts from ionospheric currents in the auroral latitudes. The DST drops around 19 to 20 of the 3rd of November 2021. And then at the same time, these aurora electrojet indexes are subjected to a huge fluctuation. We can also give an estimation of the duration of the event, which accounts for approximately 20 hours. So at this point, we are asking ourselves is if swarm observation can somehow give the same behavior. In fact, we can observe the magnetic field intensity. This time is called F minus F chaos, because essentially we have to subtract the internal field of the Earth and other effects. But as you can see, at the same a little bit around the 20th of November the 3rd, we can see a huge modulation of this magnetic field intensity. And this same behavior can be observed in field-aligned currents, which Lorenzo has already described, which are currents connecting the ionosphere and the magnetosphere, and which are strongly enhanced during these geomagnetic storms. At this point, we want to compare this data with the famous aurora electrojet indexes. As you can see, the behavior is quite similar. And if we compare this, the magnetic field data instead with Omni data, which is a compound of data from different satellites in the solar wind, we can see similarities between the behavior of the Z component of the magnetic field in GSC coordinates and the magnetic field intensity once we subtract the model. Therefore, this data from swarm satellites can be very useful, since they show a great correlation with ground-based geomagnetic indexes. And at the same time, they, because of their orbits, they can allow us to separate the analysis between the two hemispheres and separate between the dayside and nightside region when we perform data analysis. So it is a great tool to understand better what happened during interplanetary shocks, and in general to understand the physics of the interaction between the ionosphere and the magnetosphere. That's all. Thank you.
Thank you, Lorenzo and Nicola. If you have any question, please feel free to raise the hand or to write them down in the chat. Okay, at this point, I want to thank you all once again. Thank you to the organizers of this event. Thank you to all the speakers. It has been a huge pleasure to listen to your presentations, and thank you to all of you for participating. We hope to see you again to the next Redlab Live Talk. I will now give the floor to Raffaele for closing and greetings. Thank you again.
Thank you, Vivian. Hello. Thank you, Viviana. Thank you to all the speakers. And just to conclude, I just want to give you an award, which is our T-shirts. And I just prepared one slide to basically say a big thank you to all of you. And if you pass by the reception, you will get a nice T-shirt with our Redlab logo. For the people in Bologna, you will receive this by post. So again, thanks a lot for this nice afternoon. I was very pleased to see how the wide range of application and study that we are doing, from atmosphere, oceanography, and magnetosphere, ionosphere, data intelligence for archiving data on the platform. So it's very large range of opportunity that we have in our Redlab. And I'm also pleased to see that our main domains are fully covered with these interesting studies. So thank you a lot, everyone, and please pass by the front-end office to get your T-shirts. Thank you.
Thank you, Raffaele. Thank you, everyone. Have a
Thank
nice
you.
evening.
Bye.
Thank you.
Thank you.
Have a nice
Thank
evening.
you.
Bye-bye.
Thank you very much.
Thank you.
Bye.
Bye-bye.